So as the class keeps shrinking, it also becomes less and less likely that the people who are supposed to be in class are actually watching these videos. We have well over 250 students, and I suppose no more than 20 of the 20 of you in class, and maybe another 20 online are actually watching these lectures, and this reflects in your responses to the quiz questions. So and it also reflects in your responses to the homework problems and such like, because I can actually look at what you're posting, just be warned, and know if you watched the video or if you were in class, which of course means that now I bear a grudge against you for the rest of my life. Right? Just to let you know. All right. So I need this today because I've got to point a whole lot of stuff. Now, we're going to be talking about recurrent neural networks today. And if I look like this is the way to hold it, right? Anyway, here's an interesting little snippet that I picked from the web. Can anyone take a guess as to which open source project this is from? Just look at it and take a guess. So it looks like a completely authentic program, doesn't it? I mean, when I ask you this question, you're not going to tell me that that's nonsense, because it doesn't look like nonsense. It's perfectly authentic code. And here's the really cool bit. You have, everything is perfect. Every little bit of the syntax, including the comments, has been produced by a neural network. So now, yeah, but this is part of a code, right? And so you never know what else is in there. The point is, look at the stuff. Look at the fact that, look at the indentation. Look at that fact that every opened brace has been closed. Every opened loop has been closed. I mean, this thing knows, right? It just really knows. It can remember and it can know. Now, here's another example. What is this math talking about? Also generated by a neural network. Now, this is LaTeX that has been generated by a neural network, and it compiles, because what you're seeing is the outcome of the compilation, which means it's managed to produce perfectly reasonable, looking math, and even draw a diagram to go with it. And the diagram has got LaTeX commands to draw lines and arrows and such like, and they are perfectly plausible, right? It begins to falter a bit when you get to a little more tricky stuff. Like, this is text that is generated. And you have to get to the 15th or 16th word before you realize you're being fooled. So all of these are examples of data generated by a neural network. There's a very nice website by Andrej Karpathy that I recommend all of you take a look at, which says the unreasonable effectiveness of recurrent neural networks. And all of these previous examples were generated blindly by recurrent neural networks, which have been trained on different kinds of corpora. So the first example was trained on lots and lots of, I think the entire Linux source code. And then the network was made to generate text, and this is what it generated. It generated perfectly plausible code. The second one was trained on lots and lots of LaTeX, obviously, math LaTeX, and it generated what looked like a math paper, completely randomly, right? The third one was trained on Wikipedia pages, and it's even got all of the braces, opened and closed braces, which give you links. So it's created the hyperlinks and done everything. Very pretty. So now it's amazing to think that these completely plausible looking things are actually generated by a recurrent neural network. Now here's an amazing fact that I just realized yesterday. When we speak of AI and we say AI hasn't quite matched human beings yet, We are lying, right? How many of you can play chess at any level? Anyone? You, these guys, a little bit. Okay, I mean not the start beginners, but can you play a computer? Can you beat, for example, the chess game on your iPhone? No. How many of you can?
Currently, I don't think like it's a. If you
At level 0, it has levels,
okay.
right? How many of you can, right? How many of you? Okay, you play chess. Can you also play what is that? Go.
I did once. I don't think I remember the rules.
You don't even remember the rules. Okay. Can you do math?
Math.
Arithmetic, complex stuff. What is pi times pi? Can you give me the first 4 digits?
9 point something.
Just look at these. I mean, these are quite intelligent looking tasks, right? And I can create a little program using just the stuff we've got. How many of you think Donald Trump could have written that little bit of Wikipedia page? Right? So in terms of intelligence, seriously, these machines are more intelligent in using standard definitions of intelligence than about 80% of humanity. Our whole problem is that we are actually comparing them to the smart. We want them to be smarter than the smartest of us, and so we decide that they're not really intelligent. But if you look at what modern systems can do, in a couple of days they can learn to play chess better than Steve. They can learn to play Go better than any of us, and in fact the world champion, without even referring to the world. At the same time, they can learn to do some pretty fancy math, and maybe learn to manipulate robot arms, and learn to drive a car, and all of this can be done by the same system if you build it just right. And that, I think, kind of defines intelligence, doesn't it? Anyway, I'm going off track. So what we were really doing over here was modeling series. Now, in all of these, so here are a large class of problems. A situation where you must consider a series of inputs in order to produce an output. And the output to maybe either a single output or it may be a series. So some examples, like speech recognition, right? You want to analyze a recording of speech, and you want to know whether the person said to be or whether the person did not say to be. Now, you'd actually have to analyze the entire sequence end to end. And only when you get to the end, you decide, was this to be or not to be, right? So you're analyzing a series of spectral vectors, then you're outputting at the end of it a single classification output. So the input is a series, the output is a single value. Or you might want to analyze text from today's news, right? And you read the entire sequence of text, and at the end of the text, you have to decide what it's talking about. For example, if you looked at this entire series of sequence of text, after reading all of those words, how many ever there are, you might want to decide if this is talking about football or baseball, whatever else the topic might be. So now what you're really doing is analyzing a document and identifying the topic, which is to say you're inputting a series of words and outputting a single classification. Or you could be performing something like machine translation. You'd be reading a series of English words, and now you'd be outputting a series of French words. So again, a series goes in, a series comes out. So in every case, you're analyzing a series, and you're producing some output based on the content of the series. For the next 20 minutes or so, I'm going to try to use this one as an example. Analyzing the stock market. So you analyze a series of stock values over the past several days. By stock values, I'm not speaking of just one stock value. You might be analyzing many stock values, several indices, the entire market, what have you. You look at these values for the past, say, n days, whatever n might be, and based on this, you must decide today whether it's worth investing in something if you're planning to sell it tomorrow. Standard problem. Hedge funds do it all the time, right? Again, the input is a series of vectors, because on each day, or maybe at each hour of each day, you're really looking at an entire collection of values. And the output could be either a scalar, which is whether I must invest in Apple, or it could be a vector, whether I must have whether a particular portfolio makes sense. So you're analyzing a series of inputs and producing a series of outputs. Now, in order to make a decision of this kind, you have to look at past trends again, right? Which means the input has got, you have to consider a lot of what, the entire series of what comes in to make decisions. Now, before I continue, I'm going to just introduce some representation shortcuts. When I draw something like this, which is this little blue box, a couple of green boxes, and I'm going to call that color pink. I don't know what it is, right? So each of these boxes actually represents a set of nodes. So this figure is going to be something like this. So let's say I'm analyzing a vector of inputs. That vector of inputs is being fed to a complete layer of neurons. And the output of that layer is being fed to another complete layer of neurons. And that's the output of that is being fed to some output neurons. So instead of drawing the entire diagram like so, I'm going to draw them, looking at them sideways for simplicity. But anytime you see a square box of this kind, keep in mind is that it actually represents a collection, several units going into the page. So each of them is actually an entire collection. And so the simple looking diagram with 4 arrows is an entire network going up, where you have one vector connecting to another vector, connecting to another, and connecting to another, right? So if I had a network of this kind, which was looking at a vector of inputs here and another vector of inputs here, and both of these vectors fed to these this layer of green units, and that layer of green units fed to the next layer of green units, and those fed the output, I'm going to use this shortcut just to give you a clear idea of what's going on, right? Or just to be even more precise, to be even more clear, if I had a network of the kind that I have to the left, that thing is going to be simplified to the figure to the right. Again, the point being, every time you see a single square, it's actually a row of units going into the page. Yeah.
And are those layers fully connected? Is that what those are called?
Yes. So, and anytime you see an arrow, that arrow represents a potential complete connection between the vector of units on one side and the vector of units on the other side. Okay? Going back to our problem. We're trying to make money in the stock market. So how could I possibly do it? If I'm a hedge fund, I might look at what happened over the past, say, n days. And based on the behavior over the n days, I can make a prediction for today, right? And I'm going to so each day, I'm going to look at today and the past n days, make a prediction, then go to the next day, look again at that day and the past several days, make a prediction, then go to the next day, and keep doing this. So what kind of a network does this, which looks at a window, a sliding window, and keeps producing a sequence of outputs? Yeah, in this particular case, because it's sliding a long time, it's just a time delay neural network, right? Very straightforward. But then you have this problem. If I'm actually going to be using something, so you'd do something like this. If you want to look at the past 4 days, at time 3, at time t plus 3, you're going to look at time t plus 1 through t plus 3 to make some predictions about t plus 4, right? And so your predictions are going to follow this pattern. On each day, you're going to be looking at what happened that day in the past, say, 4 days, and make a prediction for the next day, right? Simple. So this is what we will call a finite response system. Something that happens today only affects the output of the system n days into the future. So the way we defined it, the y at any time is a function of the x at that time, and the x at, actually this is n, yeah, and the x over the past n days, right? The output is only dependent on the current and a certain number of past inputs. Yes? Question? No. Okay. So what do I mean by this? Again, let's say some event happened at t equals 3, as indicated by the red box. Now, as you continue to make predictions, whatever happened at time t equals 3 clearly does not affect the prediction at time t plus 2, right? But when you get to t plus 3, that red event does affect the output. At t plus 4, it continues to affect the output, as you can see from the arrows. At t plus 5, it continues to affect the output. At t plus 6, it continues to affect the output. At t plus 7, its effect is gone. So it's a finite response system in the sense that any input causes a change in the output for only a finite amount of time. Now, this kind of network, it's all very nice, but if I'm trying to make predictions, it's missing something very crucial, which is that so in this case, n is the width of the system. Now, this is kind of missing something very crucial. You define the width of the system, something that happens outside that window is not going to have any influence on your output. But now think of the stock market. Can I apply any finite window of time and say, I'm going to look at only the past 3 days and make a prediction about tomorrow? Possibly not. Some of these effects linger longer. Something that happens might have an effect, might have an influence several days into the future. So in that case, what could you do? You could go back and just extend the number of days over that you're considering, right? But this is a problem. As I keep looking further and further and further into the past, I'm increasing the number of parameters because I have more and more connections coming in. I'm considering more and more values. No big deal. I have a big enough GPU. I have enough memory. Not really. Because when you actually begin considering things, here is the kind of behavior that you'd actually see in the stock market. You're going to have weekly trends. You're going to have daily trends. The greatest predictor of what's going to happen tomorrow is what's happening today in the world, always. But then what happened 2 days ago definitely does affect what's going to happen tomorrow. But then there's weekly behavior. The stock market does not change very much on Sundays. Back in the days when they had the gigantic inflation in Germany. In fact, in most places where you have these huge inflations of thousands of %, like Zimbabwe right now, right? People are really thankful for Sundays. Because when you get some money in the morning, somebody gives you $1 million of the current currency at 9 a.m. By 9:15 a.m., it's lost its value. By 9:30 a.m., that loaf of bread that you could buy at 9 a.m. cannot be bought. These things just explode really fast. And the only time things kind of pause is when the markets stop. So you're waiting for Sundays, right? So you have actually these weekly patterns, and this is just an extreme case. But how people behave depends on the day of the week. So you have weekly trends. But then you have monthly trends. And then you have longer-term trends. You have seasonal trends. And then you have annual trends. So things are going to happen every Thanksgiving. And last Thanksgiving is a predictor of what's going to happen this Thanksgiving. But if you wanted to actually, unless you wanted to sit down and begin writing these rules, if you wanted to look at data, it means that you're going to have to look back into the past over several years to find all of these trends. That March is spring, a certain kind of stock is going to bounce up. November is about Thanksgiving, a certain kind of thing is going to happen in the market. All of these behaviors, you'd be looking at long trends well into the past. And if you want to do that with a network that's merely a simple time delay neural network, you're going to have a network such as this, which is going to have way too many parameters. What we are really looking for is an infinite response system. You want something that happens today to continue to influence your predictions tomorrow, day after, forever, except that as time passes, its influence is going to fade. Unless there's some reason to believe that these influences mustn't fade. So you want to learn all of these behaviors, but you want to have every event potentially affect the output for as long as and the influence can persist without restricting how long the influence can really persist. And that means you're going to have to look back into the infinite past. So is there an alternative to having a connections like these, where you're looking at inputs all the way into the past if you want to make predictions into the infinite future? We want an infinite response system. So you want infinite memory, right? You can have a different kind of infinite response system. Again, the idea is that something that happens today must influence the output forever, right? So here's a very simple way of doing it. I'm going to say that the output at time t depends not only at the input at time t, but also the output at time t minus 1. So in this case, what happens? Suppose I have some input at time 0. Everything is quiescent. Something happens at time 0. This is going to produce an output at time 1. But now at the next time, because I've had an output at the previous time, that is going to cause an output. So this is going to result in an output at time 1. And the output at time 1 is going to cause an output at time 2. And that's going to cause an output at time 3, and so on. So what this means is that an event that happens, say, at time 0 is going to cause an effect at that time. But that is going to cause an effect at the next time, and so on. And anything that happens at any given time is going to have an influence all the way through infinity. Now observe that what's happening over here is that the output is being fed back into the system. This is what we call a Knox network. What is the full form for it? A nonlinear autoregressive network with exogenous inputs. This was so here's a more complete representation of what really happens in a Knox network. This is, again, an infinite response system. Something that happens at any time, an input that happens at any time is going to affect the output forever. And you can see that this will happen because you can just follow the arrows, right? Something that happens here is going to affect this, which affects this, which affects this, and so on, all the way into infinity, right? Now, in this figure, keep in mind that every column, again, remember the notation. Each box is actually a network going into the page. The blue boxes represent inputs. So they could be scalar or vector inputs. The key point over here is that an input at any time continues to affect the output forever. And within each column it's basically the same function being used repeatedly, right? We're using the same function f. And to make the prediction at time t, you're just considering the input at time t and the output at time t minus 1. So which means that every single column, in terms of parameters and structure, is identical to every other column. So this is the same network as this guy, this is the same network as this guy, this is the same network as this guy, and so on. Right? Just keep that in mind. So I can sort of redraw it without actually having yellow boxes to show the output. So the brown boxes now are just the output. All columns are identical. So this is just, again, simplifying the representation. When I have two outputs coming out of a box, both outputs are the same number. Okay. Now, will this little network actually capture annual trends in the stock market? What do you think would happen over here? You guys? Someone?
I think the weight just decreases over time.
So
There's no annual.
what would happen when you're only looking at the immediately past output is that the influences are going to fall off exponentially with time, right? So although it does, any input continues to affect the output forever, the influence falls off so fast that you're unlikely to capture longer-term trends. So if you want to capture longer-term trends, how would you modify this to capture longer-term trends?
You could directly connect something from the past, as in the output of say t minus n to the current?
So the most generic case, you can actually do something of this kind. The output at time t can be computed from the past k outputs and the past k inputs. And as you increase the number of taps into the output, you actually begin capturing more and more complex interactions over time. So in the limit, this is what we will call a complete Knox network.
Isn't that the reason why we actually came up to this? Because earlier we had like CPU issues if we connect, because that was infinite. We're not doing here infinite here or something like that.
So in theory, you could be doing this, right?
Okay.
So the output at time t is computed from all past inputs and all past outputs, but we won't actually do that. What we will really do is to only use a finite horizon of past inputs and outputs, and the finite horizon is typically tends to be very short, a half dozen or so. It turns out that even this is sufficient to, if you look at the patterns. So the reason why you can just use a finite horizon and you have to look at the outputs is that if I look at, for example, the relationship of the output at this time to the relationship of the prediction at this time, target prediction at this time to the target prediction at the previous time, it shows me trends. So that means I'm capturing local trends. If I look at the relationship between what happens over 3-time instance, it's showing me second derivative trends. And so as a result, just looking over a few time steps can still give you fairly complex, very long-term trends. And so typically you will actually just look at a short horizon. In order to compute the output at any time, you'd be looking at the output in the past k instance and the input at some past m instance, yes.
Should the input and output be like of a similar kind? I mean, in the sense if the input...
Not necessary at all. So if you look at where Knox networks are used, they're used for time series prediction of various kinds. Weather. So for weather, what you might actually be doing is looking at a whole bunch of values, and you might just be predicting that it's going to rain, right? Stock markets, you might be looking at a whole collection of stock values, you might be predicting stock indices. Or you might be looking at a collection of stock indices, you might be predicting the stock value, yeah.
But the thing is, like, because the scales are so different, suppose the input is stock price and output is the number of stocks you want to purchase. The scale of input and output is so different. If you take the output from t minus 1 and the input from t, then...
What do you mean by the scale?
I mean, just the numeric value itself.
Those things, I mean, we know that if you learn these things properly, our weights should account for the ranges, dynamic ranges and such like. In fact, I'm just presenting this in a very simplified way, but if you actually went about implementing these, you'd worry about how you're going to normalize various things to make it all work, right? The key point is that there's a way of actually remembering the past. And Knox networks, it turns out, are actually fairly popular. They're used in weather, stock markets, any phenomenon where you have a distinct innovation. It's a set of innovations that drive an output. So they're the nonlinear version of what are called autoregressive models, autoregressive moving average models. Here, the key point is that we're making something, we have a way of remembering the past. But the way we are remembering the past is not stored in the network. So here is the interesting thing. The memory of the past is not in the network. The memory of the past is in the predictions made by the network. So all memory of the past is in the vice. And you're carrying the memory of the past through the vice. So instead of having to draw the memory of the past from the output of the network, let's actually make the memory more explicit. Let's make the network remember the past. So what we can do for this is to introduce an explicit memory variable whose job it is to just remember. So I could define some variable m, which is some function of the past output, what was remembered in the past. So m is the memory. So what the system remembers now is some function of what it remembered in the past. It was some function of what predictions it made in the past, and maybe a function of the state of the system that actually integrated all of this in the past. So this is the most generic statement. So MT over here would be a memory variable. and would generally be stored in something called a memory unit, and it's used to remember the past. So here are a couple of examples of memory units that architectures that use memory units. Yes.
In the previous slide, what was HFT?
Again, some system states. So I wrote the most generic version of it. Let's take a look, right? So over here, consider this. I have some input. It's producing some hidden state, some intermediate values, and those are being used to predict the output. So Michael Jordan, everybody's heard of Michael Jordan's name. One of his earliest creations was some variant of a recurrent neural network. So this is called the famous Jordan networks. And they're actually quite dumb. So the way you store memory in a Jordan network is through this explicit memory cell. And what the memory cell does is, again, remember what we said when I began talking about the basic Knox network. I said the Knox network only looks at the immediate past, so things are going to fall off exponentially, right? So if you want to remember the series of outputs over the past, instead of explicitly drawing the outputs from the past, from the k-past values, suppose I decided that I want to actually consider the predictions made from here all the way into the infinite past. Then one way you could do it is to maintain a running average of all the predictions made so far. And so the memory unit over here has only one job. It maintains a running average of all of the predictions made into the past, and that is fed into the next prediction that's made. So that would be this memory unit over here. All you're doing is you're doing some mu times the past prediction plus 1 time the current prediction normalized. So you're using a running average, maintaining a running average of what happened, and that feeds in to making the predictions at the next instant. The way Michael Jordan originally defined it, the input, all of these inputs would be the same. So xt would be the same as xt plus 1. Basically, you'd give it a fixed input and keep repeating it, and you'd let the system produce an entire series of outputs. And the input was called a plan, and the output was called an action. So I assume it was made in the context of robotics or path planning or something of that kind, right? So regardless, you could change the inputs. Different inputs would produce different series of outputs, and you could, again, train the network. But if you wanted to train the network, one of the problems that people had early on was that if you had a network of this kind, how do you train it? So because things can go all the way into the past. So they would decompose the training. And the way this was originally defined, you would still use backprop. So over here, you'd use backprop going all the way down. And the backprop is going to use this guy. And the gradient would actually not go past this term over here. So while this had a weight, so you'd actually learn this weight, you'd use backprop to compute gradients from here until here. And then this would be separate from the backprop used to compute gradients in this portion. And that would be separate from the backprop used to compute the gradients at the previous time instant. And then you'd sum up all of these gradients because this is essentially a shared parameter network. Remember, every column is identical to every other column. And then you'd perform your updates. So this was one of the first stabs at trying to explicitly capture memory in the network. L1 networks try to do something very similar, but actually they are a little even more, they are actually slightly better than Jordan networks. Here, what we do is to have a memory cell, but what this memory cell does is that it simply clones the hidden state at the previous time. And that is passed on. So now what happens is that at each point, instead of trying to just maintain a running average of the memory, of the output, or simply using the output at the previous time, you just sort of copy over whatever the internal state the network had at the previous time. And that is fed to the network at the next time. Once again, when it comes to actually learning the parameters of the network, you'd use backprop. You'd go down over here. You'd use backprop until here. And then this portion of backprop was independent of the backprop that was performed in this region. And then you'd sum up all the gradients because this is a shared parameter network. And this bit here performed a very simple task. All it did was to clone the hidden state. So you don't really need to explicitly implement that little cloning, right? It ends up literally being a conceptual sort of unit. So again, I'd like to point out over here that there's an immediate and kind of simple extension to something of this kind, in that if you just go back and look at the relation of Knox networks to Jordan networks, the Knox network was looking at the immediate past output or a certain number of past outputs, and the way Jordan networks generalized it was to maintain a running average of past outputs. So similarly, this guy could actually maintain a running average of the hidden values over past time, and this would be a simple extension to this model, right? So summary. In time series analysis, models must look at past inputs along with the current input. And looking at a finite horizon of past inputs gives us a standard time delay neural network. And if you want to look into the infinite past, you need recursion. What we mean by recursion is that it's not sufficient to simply look at the inputs. You must look at the outputs of the network, or things per terms that the network has computed, because these will persist over time. Knox networks do this by perform this recursion by feeding the output back into the network. And then you have these so-called simple or partially recurrent networks, which are typified by Jordan networks and Elman networks. These also implement recurrence either from the output or from some intermediate values computed by the network, but these are partially recurrent in the sense that when you're actually training things, when you're learning, what happened yesterday does not actually affect what I learned today, except through that one fixed parameter that I derived from it in order to make today's predictions. Backpropagation kept blocking, right? So you would learn all the way to this memory unit, and there was no gradient passed through the memory unit. The gradients would come to the memory unit, and then it would stop. And at each time, you had a local learning, and all of these were integrated for updates, right? Yeah.
I still don't get why in the previous slide we introduced the clone block in the
You don't need to. It's a virtual
Could
concept.
have just gone through.
Yeah, so the reason they just clone it is that, conceptually you're slicing out each block when you're doing the learning. That's all. Yeah.
Also, it prevents the gradients from going back.
It's just a conceptual thing. When you write code, you don't need to really clone this stuff, right? Yeah.
How would we be able to, because it says it has an infinite past horizon, but how would we detect seasonal trends? Because when we only look at the output, like the output from yesterday, then how would we detect?
So no, if I'm looking at years and years of input for prayer, on each day I know a prediction and I know what prediction I could have made. So if I were learning stuff, I'd be looking at long-term patterns, and if I were looking at a sufficient number of past inputs, but looking at these trends, if you look at the predictions made over the past several days, those trends give me an idea of longer-term trends. So that's pretty much all there is to it. Yeah.
What if, I have a problem where I only have the output for the last unit, like sentiment analysis, where I only have one output for all the words, but I don't have one SE every time step. This won't work, right?
No, I'm just giving you the basic concept. We're going to spend 2 or 3 classes on recurrent neural networks. And if you still have the question in 2 weeks' time, then I've done a bad job of teaching you guys. Right. Now, because we were speaking of partially recurrent networks, now let's try to come up with something, actually simpler and yet more sophisticated. And this is what we will call a state space model. A state space model is something that's actually used in control systems a lot, and recurrent networks are an instance of it. The system has a state, which I'm going to represent by H. And the state at any time is a function of the current input and the state of the system at the past time. The output of the network, or the output of the function, is only dependent on the current state. Now, this too is an infinite response system, because now persistence is obtained through the state, HT. Recursion, because HT is recursive, it refers to itself in the past when it's being computed. So this is a fully recurrent network. or simply we just call it a recurrent neural network, where the state summarizes information about the entire past. So if I were to draw a simple state space model, here's what it is. Now observe that this is very similar to the Elman model, right? The only distinction was, obviously there's almost a direct step from Elman models to this model. Now the distinction will come in how we learn these things. But here's how it's going to work. You'd have to define the state at an initial time. Now this would generally be considered as one of the parameters of the entire system, the initial value that you would have for the state. And at each time an input comes in, it uses the previous value of state and the input to make the current prediction about the state. And that is being used to predict the output. And then at the next time, that value of the state and the current input predicts the state, and that predicts the output, and so on. So at each time, the system state is predicted recursively from itself and the input, and the output is based on the state. And observe that although I've just drawn one little square for the state can be arbitrarily complex internally. So my state itself could be represented by a fairly complex function, which might be, for example, several layers within a neural network. So again, when I'm specifying my initial value for the state, it means that I'm going to have to specify initial values for every component of the state. That's what my h minus 1 would be. The h minus 1 is present because you have a recurrent structure, you have a recursive structure. Initial values must always be specified. In the absence of initial values, the structure is not completely specified, right? So here's what I would have. Now, if I want to expand it out and draw it explicitly, which we really won't for most of it, we're going to, after today's class, I won't spend a lot of time trying to draw explicit structures for the hidden state. But just to give you an idea of the kind of structures that you might have. You might have, for example, this could be a neural network. This entire machine could be a neural network where at each time, this is a simple multi-layer perceptron maybe. The input goes in, you have one hidden layer, and the hidden layer goes into is used to make the predictions, and the hidden layer refers to the input and to itself in the past. So now the state is represented by the hidden layer of the network, right? Which is why I'm using the boxes that we use to represent neural networks. Or I could have a network where the state is actually comprised of two hidden layers or more hidden layers. And each hidden layer, a simplified version, each hidden layer could refer to itself in the past and to the hidden layers at the current instant lower down the network, right? So this guy, the first hidden layer looks at the input and at itself in the past. The second hidden layer looks at the first hidden layer and at itself in the past, and so on. Now you have the state and you have the output, which depends only on the final hidden layer. So I could make things even more complex, right? All of these still follow the same basic idea, right? Here I have this hidden state. So the first hidden layer looks at the input and at itself in the past. The second one looks at maybe both the input and the lower hidden layer and at itself in the past, and then you have the output. I can make the structures, or I could have a structure like this one. Yeah.
What is the purpose of this? Aren't you expecting like the first hidden layer to capture the trends in the input essentially and then passing it to the second hidden layer?
You know, the first input, it's just abstracting some information from the input. The whole point of having these guys look at themselves in the past is that the information it extracts in the input from the input is relative to what it already knew in the past.
The skip connections.
The skip connections. I'm just saying that these networks can be arbitrarily complex, and given that you're just increasing the complexity of the function itself, and each of those would have a purpose. If you actually went through the math and analyzed it, you can show how each of these causes different effects and the kind of things that you can learn. But as far as these things are concerned, it's just a neural network. You know how all of these structures are, right? So I might have structures like these. Now observe that I have things going from the top back down, things from the bottom going up. It's fairly, it can be, you can draw it draw an arbitrarily complex network, you can even have outputs coming back from the input. The only point being that the predictions at any time are based not only on the current inputs, but also what happened in the past. You could be looking just at the immediate past, like so, right? Or you might even be looking at multiple instances into the past, like so. Again, every column is identical to every other column. I'm just showing different degrees of complexity of the overall structure, recursive structure that we've got. The underlying concept remains the same. We've introduced a recursion, which allows the structure to remember things about the past, and so retain memory about what it knows of what happened in the past and what it predicted in the past in order to make the current predictions, right? So practically speaking, the most simple structures are the most popular. You're going to have structures such as these. But in theory, anything is possible. When I actually draw these diagrams, I will often use simplified representations such as this one. So that arrow that goes back really doesn't mean that the output of the unit is going back to itself. You'll see figures like these in the literature very frequently. This doesn't mean that any network input feeds back to itself. What it really means is that there's a recurrence from that unit to itself. So for example, this little figure over here actually represents the recurrent structure shown at the bottom. Or something like this represents the recurrent structure shown at the bottom, right? So the point is we have this very simplified recurrent structures that are being shown where, again, although the figure itself shows loops going back in, this is really strictly a feed-forward structure. When you actually explicitly draw out the kind of structure that is used to make predictions, you have many columns of inputs, and the information is flowing strictly left to right. So the input is purely feed-forward. There is no looping going on, right? Now, let's look at the kinds of computations that would be performed. Let's take the simplest structure, where I have one hidden layer, and that hidden layer feeds back to itself at the next instant. So I have recurrence over the hidden layer. I'm using colors to show recurrence. So the red loops represent recurrence. Now, what kind of computations would we have in a network such as this? So you'd have some initial values for the hidden layers, which represent the state. These are going to be some parameters of the network itself, which would be learned. Again, these are learned parameters. Now, the hidden value at any time, so the superscript 1 just tells you the hidden layer number. The superscript is the number of the hidden layer. It's going to be some weighted combination of the input, where these weights are specific to this connection, shown by the superscript 0, indicating that it's connecting to the 0th layer of the network, which is just the input, plus some weighted combination of the hidden layer in the past time. So it's going to be looking at some weighted combination of itself in the past time, which means that the h of t is some function of the weighted combination of h of t minus 1 plus, of course, the bias. So the overall prediction at time t is some activation applied to a weighted combination of the inputs plus some weighted combination of the hidden values of the past time plus some bias. The output is some activation applied only to the hidden values at the current instant. That is for this specific architecture, where the recurrence is only over the hidden unit, right? So suppose I just expand this little structure and gave you 2 hidden layers. This is what it would look like. So here, again, now I have 2 hidden layers, so both of them must be specified when I specify the initial values for the network. And both of these would be parameters of the system. And then for this guy, this is going to be some activation F1 applied to a weighted combination of the x's plus a weighted combination of itself one time step in the past plus some bias. That's basically what this equation here is showing, right? a weighted combination of the inputs plus some weighted combination of itself, one time step in the past plus a bias. The second term, the second layer of hidden units are going to compute some other activation of some weighted combination of the hidden units in the first layer, as per this diagram, plus some other weighted combination of the hidden units in the next layer of the same hidden units, one time step in the past. So this is the recursion, plus a bias. So this term here this is for 2. It's a weighted combination of H1 plus a weighted combination of H2 in the previous time instant plus a bias. And then finally, again, you have the output, which is just some activation applied to a weighted combination of these guys. Again, keep in mind that all of these are really vectors. I've shown you a little square, right? So what this really means is that I'm stabbing my own microphone. Anyway, when I have this little equation over here, hi1 of t, it means that there are many of these equations representing every single node that's going into the page. It's not just one single term, right? So also this guy over here represents several units going into the page. And the output too, you might have multiple outputs going into the page. So when I speak of this connection, when I speak of these weights, what I'm really saying is that this H2 is not just one little box. Again, I've said this in the past, but it's worth remembering that what I've shown as one H2, like so, is actually an entire collection at that time, which is looking at the entire a weighted combination of all of these guys and a weighted combination of all of these guys. I've just represented the entire thing using one equation, just to be very clear, right? So that equation is actually a complete vector equation. So also, if I were doing something like this, you can easily guess what the predictions are going to be. So this fellow over here is going to be some activation applied to a weighted combination of the inputs and itself in the past. This one is going to be some activation applied to a weighted combination of these guys, the inputs, and itself in the past, and so on, right? The arrows should give you a complete indication of what kinds of connections I have and how the actual operations are to be performed. And at each time, keep in mind that when I just write one equation, I'm actually writing a set of equations because that square box represents many units. Someone raised a hand, yeah.
So it is a variation of the RNN, or it's a mix of the resonant and RNN here? Because you have the extra connections between each layer.
Having a skip doesn't make anything a resnet. So skips of this kind. We've been talking always about layered networks, but there's nothing sacrosanct about layers. You can have input. So there's no notion of a residual over here. It's just that it's just a standard structure where you're looking at many inputs. Again, the key point is that you have some hidden values, H, which are represented by the green boxes, which depend on the input and themselves in the past, and potentially also on past predictions, although that's very unusual, and the predictions which depend on the hidden values and maybe also on the input. Now, typically, you don't actually make the output dependent directly on the input because it doesn't. The inputs are captured by the hidden units. So here are all the kinds of structures that you might actually see in the big picture. So you may have one-to-one where these are all images taken from Karpathy's page. A single input produces a single output. Now you're all familiar with this. This is what we've been looking at from the very first class. If I expand the structure using these boxes to this kind of representation, this is just a simple MLP. The first figure is just a standard MLP, right? This one is a one-to-many, where I have a single input coming in, and it produces a series of outputs, right? This is where a many-to-one, this is like the speech recognition problem I just showed you earlier. You look at a series of outputs, it produces a single input. All of these are different variants of the same underlying structure. So this would be like looking at an entire passage of text and determining the topic. Or you might have something like this, where you look at a series of inputs, and then when you've done absorbing the series of inputs, you produce a series of outputs. This might be, for example, something you would do if you were translating language. You look at the entire English sentence and then decide how you're going to generate the entire French sentence, right? Or the one to the right, where the output is many to many. At each time, you look at the input and you produce an output, and they're kind of synchronous. All of these are different variants of the basic notion of recurrence. The number of inputs you have you might not actually have information flowing across time instance. You might have information flowing across time instance. The number of inputs and outputs need not be the same. They need not be any kind of time. The inputs and outputs might be time synchronized or not. All of these variants come under the generic umbrella of networks with recurrence, in that a single input can produce an output forever. So these are recurrent neural networks. Questions? So again, to summarize, time series analysis must consider past inputs along with the current input, and because it's looking into the infinite past, requires recursion. And Knox networks do this by feeding the output back to the input. Simple recurrent networks, those are the first ones we saw, maintain separate memory or context units to retain some information about the past. But the more comprehensive model are the state space models, which employ some state variable and store information recursively through the state variable. And output is, and these are fully recurrent networks. And state space models enable current error to update parameters in the past. Why? Because an input at any time affects the outputs all the way into the future, which means that if the network makes an error, if you have an input now, and the network is correct for the next 5,000 instances and then produces an error, that error too is a signal that can be used to come back and affect how the current input must vary in how it produces how it affects the computation. Yes.
What's the difference between an Elon network and a state space?
The Elman network, you mean? So the Elman network was, the primary difference was in the way you learned stuff. So in the Elman network, if you had an error in the 5,000th time instant, it didn't tell you about how the input at time 0 caused. So when you were backpropagating stuff, that error was not backpropagated all the way back to the beginning to decide how this influence must be modified.
And that's because we're taking the backpropagation through the states in a state space model.
So no, exactly. Whereas there you just sort of blocked it at the memory unit, right? So the memory units, and it's now you have to go back a little bit in time, in that you're looking at a time when computation was not cheap, and people like to decompose things. So both in Jordan networks and Elman networks, these memory units blocked the flow of information both backward and forward. Now, the whole idea of these networks is that as you're going forward, if you just store these state units, you don't need to store anything about what happened prior to the state units, because the state units that are used to make future predictions are all that are required, and that is complete. So as you're going forward, the computation is always, the amount of information you store is always limited. So in Jordan networks and Elman networks, they also wanted to have the same characteristic during learning, and that you could just take one step, make a prediction, make some corrections, forget about everything else you did, then take the next step, and keep repeating the process, right? Whereas if you want to have the complete state structure, now if during learning you have to remember the whole thing, because something that happened here could cause an error out there, and you're going to have to pass that information all the way back to the very beginning to see how this influenced the output. Right? Yeah. Yes?
I'm not sure if I get this right, but for the space models, are we when you say it updates the parameters in the past as well. Are you talking about that we are using the same network to train the data from the past and from today? And when we are updating the parameters for today, then we are also updating the data parameters.
So what happens, think of it this way, right? When I actually think of this figure. So if an error happens out here in this network, I'm able to compute how a small change in this guy affects that error, right? And how a small change in this weight would have affected this error. So in that sense, so if you're actually during the process of learning, you need to know exactly what to attribute the errors to, and you can attribute an error at any time to anything that happened all the way to the infinite past. Whereas the memory structures that we saw earlier, the simpler structures, could only attribute it to what has been stored right now because no information was sent backwards. So in terms of engineering the solution, if you want to perform any kind of learning on these networks, you're going to have to store all of this information. You're going to have to come all the way to the end before you begin learning everything about the network. Whereas in the memory structures, you'd have some current memory, you make a prediction, you get some error, you can use those backwards to learn something about your parameters, and then you toss the whole thing away because even during the learning phase, the only structure the structures that you're looking at are very local. The memory structure plus the current processing.
Just to be clear, so each of those the columns are independent networks, right?
All of them are identical networks. Every column is identical to every other column, right? So, yeah. It has to do with the computational, yes.
You answered my question.
Yes. So every column is identical to every other column. Now the difference is really what happens during learning. That over here, if you want to learn, then you have to store the entire sequence of operations because it's really one giant feed-forward network, right? Whereas in the other structures, the idea was that the memory captured. So again, during the forward pass, remember that I don't need to store these guys. If I have just this fellow, that is sufficient to compute y2, right? And thereafter, I just need to store this term, and that is sufficient to compute y3. I can throw away, discard everything that happened in the past. But in the backward pass, that is not true. I have to pass the information all the way back. So if you're learning something, you're going to have to remember pretty much all of this in order to make the right attribution for what caused the error. Whereas in the memory structures, you would just look at just this portion of the network, and you could compute some gradients over just this portion. And then when you get to the next time instant, you're just going to look at this portion of the network because you're throwing all the rest of it away. Even the learning is performed very locally. So can you just tap that lady on her head? Please wake up. Okay. So yeah. Question?
Yeah, I'm still a little bit confused because it seems that while they're still in identical networks, they're still coupled in time. So we'll update the t-1th time instant and then the t-2, t-3.
Think of it this way, right? So what we would do is something like this. I have some memory structure. This memory carries everything about the past, right? So during the forward pass, these two are going to affect the prediction. If I make some error, I can compute gradients here, here, and here, and that's fine. Then at the next step, I'm going to assume that I have a memory block, right? I cut this out and threw it away. And now I have a completely independent prediction where this guy is going to cause a prediction like this, and there's an error. And then you just make any learning you've done learning you're done is done locally over this network without any reference to what happened in the past, because the notion is that the memory carries everything, right? And this is fixed. You're ignoring the fact that something that happened here actually affects this memory. So this was the old memory structure. So you thought of many local computations, which were nevertheless aggregated when you computed the actual derivatives. Whereas in this full structure over here, you actually keep track of the fact that I can wiggle this parameter there without wiggling the corresponding parameter here. And that's still going to affect everything, right? So you're actually thinking of it as a completely unrolled but shared parameter network over here. That's the basic difference. Anyway, so where's my sword? So how would you train this network? Questions? Now, training this network actually ends up becoming quite dramatic, really. Because what happens is that when you actually think of the entire computation, the actual network that you're using to make your series of predictions is this complete unrolled network, right? You have a sequence of inputs coming in. You have a sequence of predictions being made. But this is really just a standard. I mean, if all of those units were just perceptrons, this is just a standard multi-layer perceptron, is it not? I mean, if I drew it sideways, this would look like all the multi-layer perceptrons I've always been drawing in class. The only distinction is that every layer in the perceptron is also producing a separate output. So this is really no different from, say, having a figure like this. So this is the kind of structure that we've been drawing in class all along, right? This is the kind of structure that we've been drawing in class all along. And we've been saying that this is your y, and you'd have some desired output d. You could use a computer divergence and use that to back propagate all along, right? This is exactly the same network. The only distinction being you're constraining that these guys, actually, I can think of it this way. I can have a second set of inputs feeding these guys, right? And this is just the MLP that you've seen before, exactly the same. The additional constraint is that these weights and these weights are identical. Okay? I can also do something of this kind where I say these guys produce two outputs. So this is some other y over which I have some desired value. Right? This is just the standard MLP that we've always drawn. And now when I draw the MLP like this, and the additional constraint I'm going to have is that these weights are the same as these weights, right? So this is a standard feed-forward network end-to-end, going from the beginning to the end. So although I've drawn it sideways, keep in mind that this is just a standard feed-forward network. And this is what you'd actually be performing back propagation over. So Christine, you're looking puzzled? Did I lose you? No. Okay. So this is what I'd be performing back propagation over. So here's what you're going to have. You're going to have a collection of sequence inputs where I have a collection of this kind where each sequence is like this, where each sequence I'm going to have several training instances. Each training instance is going to comprise an input sequence, a sequence of input vectors, and an output sequence, a sequence of desired outputs at each time. I have several of these. And then the network is going to make a sequence of actual predictions. And I'm going to train the network to minimize the error between the sequence of actual predictions and the sequence of desired predictions. So the way to think about this is, let's say I have a forward pass. Now, I just pass my input through the network. Basically, I'm following the computations shown in the figure. Right? I'm going to generate all of my y's. Now, at each time, during the backward pass, I'm going to compute gradients of the error of the actual outputs with respect to the desired output and pass them backward in order to perform gradient descent. Now, just for simplicity, I'm actually going to sort of draw things like this just to make things much more explicit to show you how things actually connect up. So although I was drawing sideways lines so far, what's really happening is the same output is going both here and here. So this is just sort of making that more explicit, right? These curved lines are ugly, but they actually represent what's happening much more clearly. Now, what is the error we would compute? The error we would compute is the error between the sequence of outputs produced by the network and the sequence of outputs desired from the network. So this is not just the sum of the divergences at each prediction. It is an error that's defined between the one entire sequence and an entire sequence. It's a function of two sequences. It's not the sum of the functions of n independent errors. Do you see the distinction, right? So this is very important to remember. Yes?
So in this diagram, you would learn three sets of weights, right? One coming out of XO, one coming from the previous hidden state, and one feeding to Y.
Yes.
Right?
Yeah. And eventually you'd also learn this guy. Don't forget H minus 1. H minus 1 is the initial state of the system. That must also be learned. So, okay?
H minus 1 is also a parameter.
It is also a parameter. Because how do you define the initial state of the system? What is the best way to initialize the system? That is something that's also learned.
So backpropagation is not unrolled in time. That happens just once.
Meaning?
So like we are computing y0, y1, y2 at different time steps. Eventually after yt is produced, is backpropagation happening for all the layers together? For all the
Because you have to complete all of the computations, correct?
Right.
So this was the key difference between these networks and the memory cell-based networks, where at each time you could just perform a local backprop and keep moving on. That's not what we're actually doing over here, right? So this, again, the key point is that you're looking at a divergence between a sequence of predicted values and a sequence of target values. And these divergences may not be the sums of individual, the errors at individual time instance, unless you actually define it that way. For example, I might be making a prediction that is a text sequence. The output might be a completely different text sequence. Now these two could be error, the error is going, if I begin looking at something like the string at a distance, that's not just looking at the current outputs and making comparisons of the current outputs. It's actually looking at a function of both, right? So the divergence, the key point to remember over here is that the divergence, we want the divergence to be differentiable, but the divergence is a function of two series. It's not the sum of n individual divergences unless we actually define it that way. And so I'll continue in the next class, but it should be fairly straightforward to intuit what really happens. In fact, let me just 3 minutes. Let's give them 2 minutes of a heart attack. So I have the slides over here actually talk about everything. They present everything both as in scalar form and in vector form. I'm going to focus on the vector form and explain of backpropagation when I explain these. So notation, x's represent the inputs, y of t represents the output at any time. The z1 represents the input to the activation of y, the input to the output activation. The output activation, again, could be a vector or a scalar activation. It could be a softmax, right? And then ht is going to be the output of the hidden system. Z0 is the affine combination that is fed to the activation of the hidden layer to produce the output. So all of the variables are clear, right? So here's how I could actually do this. The very first step, I'm going to have to define the divergence of, sorry, the derivative of the divergence with respect to each of the outputs of the network. Although the output of the network is a sequence, and the target output is a sequence, and the actual divergence is a function of two sequences, I can nevertheless still compute the derivative of this divergence with respect to each term, so long as the divergence is a differentiable function. If it's not a differentiable function, we're going to have to come up with approximations that make it a differentiable function. So we're going to assume that although the divergence is a function of all outputs, we can compute the partial derivative of the divergence with respect to each of the outputs, right? I've shown this as a partial derivative. It's really going to be a gradient. It's going to be a vector because if you have multiple outputs. And now let's take a look at how we compute our derivatives. So at the very first time instant, I can just compute the derivative with respect to this z by just post-multiplying the derivative of the divergence with respect to y by the derivative of the activation function. This term is a Jacobian, right? Which is the derivative of this activation function, which is typically a vector activation like a softmax, but doesn't have to be, right? Now, once you do that, I can backpropagate it one step back, and now I can compute the derivative with respect to the output of the hidden layer, which simply multiplies the derivative over here with the weights. We know exactly how to do that. Now, in the process, we are going to use this old trick that if I have a vector h, if I have a vector x, y equals w times x, where y and x are vectors, then the gradient and I have some divergence of, which is a function of y, then the gradient of the divergence with respect to w is simply going to be x times the gradient of the divergence with respect to y. We saw this several classes ago, right? So I can use this little rule to compute the derivative of the divergence with respect to the weights out here. Now keep in mind, note this. This is the derivative of the divergence with respect to the weights out here. And I just do this using that simple rule above, right? And now let me quickly work my way backwards. Now that I have this guy, I can compute the derivative with respect to the divergence to the derivative with respect to the z that's input to the hidden layer. I can compute the derivative with respect to these weights, also applying the chain rule. And now I can also compute the derivative with respect to the weights that connect the hidden units in the final column with the hidden units in the previous column, right? All of this is very simple. So I'm starting with the last column and working my way backwards. We know what to do at the last column. Now let's go to the next column. At the next column, again, I can work my way down the column. I can compute the derivative with respect to the input to the output activations. And then here's what happens. When I compute the derivative with respect to the output of this hidden layer, I must now actually combine two terms. I must add two terms. Because if I modify this output a little bit, it changes the error through two paths. One is upwards, the other is this way, right? So the derivative over here of the divergence with respect to the output of this guy actually sums the derivative that you obtain straight down at t minus 1 and the derivative that you get through this path. Two guys, right? So, and then here's a third one, which is also very important, namely that when I compute the derivative with respect to this weight, I can independently compute the derivative of the divergence with respect to this weight, but I know that these weights and these weights are identical, right? And I have already computed the derivative of the divergence with respect to these weights. These are shared parameters, so I just add the current derivative. to compute the overall derivative of the divergence with respect to the weights. And so I can keep working my way backwards. I can now use the same, I can compute the derivative out here. Again, when I'm computing the derivative with respect to the weights below, I've already done this once at the next instant. I just have to add the local derivatives on. So there's a summation over here that I'm actually performing. I'm actually adding the derivatives in, right? So because these are shared parameter networks. And I can just keep working my way backwards. Now I can compute, when I compute the derivatives with respect to these weights as well. Again, I've already done it once in the future. So I'm actually going to add the local derivatives to it because these are shared parameter networks. And I can quickly use the rules that I've had over here to pass my differentiation all the way back to h minus 1. Okay? So we'll stop right here. We'll spend a little time on this tomorrow or in the next class and actually look at issues like stability and so on of how well these things operate in the next class. Thank you.